A photon does not choose between being a spread out wave or a localized hit. It manifests both descriptions at once, and only your measurement selects which face becomes visible. This isn't indecision. It's a structural collision between how reality behaves and how you expect it to reveal itself. Wave-particle duality is the moment that collision becomes undeniable. Picture a single electron leaving a source and moving toward two thin slits. You'd assume it travels through one slit or the other, like any small object. But the detection screen betrays that assumption. A lone electron builds an interference pattern over time, as if it explored multiple paths simultaneously. You can almost feel your expectations compressing under the weight of that result. The twist is immediate. Nothing in your everyday intuition survives this observation intact. Now imagine placing a detector at one slit just to check which path the electron really took. The interference vanishes. A clean particle-like distribution appears instead. Your act of probing collapses the very behavior you tried to clarify. What exactly did you measure? A path or the limits of your own conceptual framework? The moment you look, the phenomenon reshapes itself around your question. You might feel the urge to reduce this to a mere measurement glitch. Resist that. Quantum mechanics predicts this dual structure with perfect consistency. The wave function spreads, the detection is discrete. One description governs evolution, the other defines outcomes. You're watching two incompatible lenses reveal a single system that refuses to fit either one alone. The deeper you examine it, the more it exposes the fault lines in classical reasoning. And here's the fracture that should unsettle you. The electron is not switching modes, you are. The boundary is not in the particle, it's in the question you ask. Consider what the interference pattern actually encodes. Not a trajectory, but a probability amplitude that evolves according to Schrödinger's equation. This amplitude is not a mist of physical stuff drifting through space. It's a mathematical structure, dictating how likely different outcomes become when you finally observe the system. Yet the pattern behaves with the precision of a physical law, as if the electron's presence extends across mutually exclusive possibilities. You're watching a rule book that refuses to map onto any single, definitive path. Imagine rendering the setup in slow motion, slit to screen. The amplitude flows like a fluid, divides cleanly, recombines sharply, and produces interference that no classical particle could generate. If you tried to assign the electron a hidden trajectory threading through this fluid, inconsistencies erupt immediately. At some point in that imagined reconstruction, you must choose whether to preserve locality or preserve realism, and either choice fractures your expectations. Where would you place yourself in that decision? Now shift perspective. Instead of asking what the electron is, ask what the wave function permits. Quantum theory specifies how amplitudes interfere, how they accumulate phase, how boundary conditions reshape their evolution. It does not commit to a tangible, spatial entity occupying both slits. Instead, it commits to the predictive structure itself. The electron is localized when measured not because it converts from wave to particle, but because measurement forces a selection among incompatible amplitude branches. The mechanism is relentlessly precise, yet conceptually disorienting. Here's the disquieting implication. The duality arises only when you attempt to reconcile two incompatible models, propagation and detection, into a single, seamless picture. The phenomenon doesn't bend, your categories collide. And if you trace that collision far enough, you realize something uncomfortable. Your intuition demands a story that physics doesn't supply. You're left holding a question that tightens rather than resolves. What exactly do you think the electron is between the moments you look? Shift the frame again. Instead of the electron moving through the apparatus, imagine the apparatus shaping the space of possible outcomes. The slits, the spacing, the distance to the screen, each element defines constraints on phase, not on position. What travels forward is a rule-governed evolution of amplitude, not a tiny object picking a lane. This inversion is subtle, but once you notice it, the usual picture of a particle deciding a path collapses instantly. You're not watching motion in space, you're watching the architecture of possibilities sculpt the event you eventually record. Picture a version of the experiment where the slits slowly narrow as the electron approaches. The amplitude adjusts continuously, redistributing itself so the interference fringes widen. No classical particle could pre-adjust to a geometric change it has not yet reached. Yet the prediction unfolds flawlessly. You might try to visualize this as an extended wave adapting to new boundaries, but the instant you do, a tension appears. This wave is not a physical surface, yet it behaves as if it carries information about global conditions. Where, in your worldview, does such coordination fit? Now bring yourself into the frame. If you placed a detector near the narrowing region, the behavior would shift abruptly. Instead of adaptation, you obtain localization. Instead of fluid continuity, you get a discrete impact. Your presence alters what the rules allow to unfold. Not because consciousness intervenes, but because measurement forces the system into a form that cannot sustain interference. The moment you interact, amplitude branches become mutually exclusive outcomes. What was fluid becomes definitive. This shift points to a deeper structural asymmetry. Evolution is wave-like, outcomes are particle-like, and the two descriptions cannot be merged without contradiction. The phenomenon tolerates both, but only in different phases of its existence. And the unsettling part is this: the transition is not gradual. It snaps into place the instant you ask for certainty. Start from a different angle. Ask how the system encodes information before any measurement is made. Quantum theory gives a precise rule. The amplitude evolves linearly, allowing multiple, mutually incompatible possibilities to coexist without conflict. This coexistence is not metaphorical. It has measurable consequences. Yet none of these possibilities can be extracted directly. They influence each other, but they never appear side by side on your detector. You're dealing with a structure that computes outcomes without ever committing to one until you force its hand. Imagine isolating a single amplitude branch. For instance, the part that would correspond to the electron passing through the upper slit. If you try to block the lower slit and preserve only that branch, the interference vanishes immediately. But if the lower slit remains open yet unmeasured, the additional branch influences the final distribution even though you never detect its presence directly. This is like removing a path you never witnessed and watching the final pattern deform. Where in your understanding does unobserved structure acquire such leverage? Now push this further. Suppose you tune the apparatus so that the two paths differ by only a tiny phase shift. The interference fringes slide smoothly across the detection screen. A minuscule modification in one branch affects the entire pattern, including regions where that branch contributes nearly zero probability. The influence is non-local in effect, but not in signal. Nothing travels faster than light, yet the whole configuration responds as a single computational object. If you place yourself in this scenario, where do you locate the real state of the electron? In the screen, the slit, or the unseen amplitude you can only infer. This leads to a stark reinterpretation. What you detect is not the full structure, but the final projection of all competing possibilities. Measurement compresses a rich, extended evolution into a single event that erases its own history. And after recognizing that, one conclusion presses in from the edges. The thing you observe is only the residue of everything you never saw. Shift focus to the act of measurement itself, not as a passive reading, but as a physical interaction that rewrites the system's allowable states. Before you measure, the evolution is linear and reversible. After you measure, it is abrupt and selective. This asymmetry is not a minor detail. It means the rules governing how the system changes depend entirely on whether you decide to extract information. The laws themselves pivot around your intervention, revealing a divide that classical reasoning cannot reconcile. Picture a detector with adjustable sensitivity placed just behind one slit. At minimal sensitivity, interference remains mostly intact with only faint distortions at the edges. Increase the sensitivity slightly, and small ripples appear across the interference pattern. Push it further still, and the interference collapses entirely. You haven't touched the electron directly. You've merely increased the amount of information the detector could acquire. And yet the pattern undergoes a phase transition, as if your potential knowledge reshapes the system's evolution. If you were supervising this setup, where would you locate the boundary between weak influence and full collapse? Consider what this implies. Quantum mechanics ties the act of gaining witch path information to the destruction of coherence. This is not a statement about disturbance, it is a statement about compatibility. Path knowledge and interference are mutually exclusive descriptions. Gaining one eliminates the other. The dual structure persists only when the paths remain indistinguishable. The moment they can, in principle, be told apart, the system reorganizes into discrete outcomes. You're witnessing a logic that prioritizes informational constraints over spatial intuition. This brings us to a deeper inflection. The system does not encode a single underlying reality waiting to be uncovered. It encodes a set of potential realities, each incompatible with the others, and measurement selects one by eliminating the rest. That selection isn't a reveal. It's a rewrite, and once you grasp that, a sharper thought emerges. The electron's path doesn't vanish when observed. It never existed before you looked. Approach the structure from an information flow perspective. The evolution before measurement carries phase relations, while the outcome after measurement carries only discrete values. The transition between these two regimes is irreversible, not because energy is lost, but because information about relative phases becomes inaccessible. Once that information is gone, no operation can reconstruct the interference pattern. You're looking at a physical process that deletes context so thoroughly that the system cannot remember its own continuity. Imagine performing a delayed choice modification. You let the electron pass the slits, allow the amplitude to spread and overlap, and only then decide whether to insert a witch path detector further downstream. If you choose not to insert it, the screen records interference. If you choose to insert it, the pattern dissolves into particle-like hits. The sequence of events challenges the idea of a fixed trajectory. The electron cannot retroactively change its path, yet the observed outcome shifts based on a decision made after the supposed path should already exist. If you were responsible for that choice, where in time would you anchor the moment the electron acquires a path? This forces a reframing. The system does not store a hidden history. It carries forward a set of correlated amplitudes sensitive to future measurement contexts. These correlations are not causal signals. They're constraints on how probabilities must cohere across time. The measurement you perform determines which correlations remain meaningful and which are discarded. Your observation doesn't reach backward. It narrows the structure forward, collapsing incompatible branches and preserving only those consistent with the information you extract. From this angle, dual behavior is not a mysterious oscillation between forms. It is the system obeying two rules that cannot operate simultaneously. One rule maintains coherence, the other enforces definiteness. Measurement forces a transition from one rule to the other, and the collapse marks the boundary between them. And once you see the boundary clearly, a sharper realization settles in. Certainty is not something the system reveals. It's something you impose. Shift attention to the role of distinguishability itself. When two amplitude branches are perfectly indistinguishable, they interfere. When they differ in any measurable way, they decouple. This is not an aesthetic feature. It's a structural rule. The universe does not care which path the electron took. It only cares whether the paths could, even in principle, be told apart. The moment distinguishing information exists anywhere in the environment, the branches stop interacting. You're watching reality enforce a criterion more abstract than geometry. Informational separability. Imagine the slits are identical except for a tiny polarization tag applied to one path. A tag you never read, a tag you may not even know exists. The interference pattern disappears instantly. Restore indistinguishability by erasing the tag before detection, and the interference reappears as if it had been waiting beneath the measurement. To you, the tag seems irrelevant because it never enters your awareness. But to the system, the mere possibility of extracting that information reshapes its evolution. If you were adjusting that tag, how would you decide whether you were modifying the system or merely modifying what the system is allowed to express? This exposes a deeper mechanism. Coherence and decoherence are not mystical transforms. They are bookkeeping rules about what counts as the same history. When two histories cannot be told apart, they merge and interfere. When they can be told apart, they separate and behave classically. The electron isn't choosing, the environment is partitioning possibilities into non-overlapping narratives. Measurement is simply the most extreme version of that partition. Yet here is the element that should unsettle you. The crucial difference between interfering histories and separated histories depends not on physical disturbance, but on informational accessibility. Remove the possibility of knowing, and the universe recombines what looked irrevocably split. And that leaves you with a sharper question than before. Where exactly do you draw the line between what is knowable and what is real? Start by examining the system from the environment's perspective, not yours. Every interaction, a stray photon, a vibrating molecule, a microscopic thermal fluctuation, can imprint faint traces of which path information. These traces diffuse outward, not as signals, but as correlations that gradually lock amplitude branches into separate, non-interfering narratives. Decoherence is the process that amplifies those correlations until interference is no longer physically recoverable. You're watching the universe sort possibilities into compartments long before your detector ever enters the scene. Imagine placing the double-slit apparatus inside a cold vacuum chamber, shielded from light and insulated from vibration. Under those conditions, interference emerges cleanly. Now heat the chamber slightly. Thermal photons begin bouncing off the electron's possible paths. Each scattering event carries a whisper of distinguishability, and the interference fringes blur, then disintegrate. Nothing collapses in a dramatic sense. Instead, coherence evaporates as the environment accumulates information you never see. If you were asked to pinpoint the precise moment coherence becomes unrecoverable, could you do it? Or does the transition resist any single definitive boundary? This reveals an uncomfortable symmetry. The environment performs countless weak measurements that you never register, and each one chips away at the system's ability to maintain overlapping histories. The classical world you inhabit arises from this relentless erosion. What you call a particle is simply a quantum object that has lost the capacity to keep its alternatives coherent. The more tightly it is entangled with surroundings, the more classical its behavior appears. Your experience of definiteness is not fundamental. It is accumulated decoherence made visible. But look closely at what this means. The electron's dual behavior is not exceptional, it is the default. The classical picture you rely on is the exception, produced by environmental surveillance so pervasive you mistake it for intrinsic structure. And once that sinks in, a sharper insight surfaces. Your certainty about objects is just the environment's memory, not the world's essence. Consider how entanglement reshapes the question entirely. When a quantum system interacts with any other system, a photon, a detector, even a microscopic grain of dust, their states no longer stand as separate descriptions. They form a joint structure in which neither component possesses an independent set of properties. The electron's wave-like evolution and its particle-like outcome become inseparable from whatever it interacts with. You're no longer asking how one object behaves, but how correlations distribute across an entire network of possibilities. Imagine linking the electron's two possible paths to a tiny auxiliary qubit positioned beside the apparatus. One path flips the qubit, the other leaves it unchanged. The electron never touches the qubit again, yet the final interference pattern collapses instantly. Restore the qubit to its initial state through a precise operation and interference returns. You altered nothing about the electron directly. You only manipulated the correlations between them. If you were responsible for those operations, questions would you attribute the disappearance of interference? To the electron, the qubit, or the relationship between them? This scenario exposes a deeper constraint. Quantum outcomes depend on the structure of entanglement, not on the behavior of isolated entities. Interference requires unified amplitude branches, but entanglement separates those branches across multiple systems, distributing information in a way that forbids recombination. Measurement is simply the extreme case in which entanglement becomes macroscopic and irreversible. What looks like a sudden collapse is the expansion of correlations beyond any practical ability to reverse. Follow this reasoning to its edge. The distinction between here and there, wave and particle, path A and path B, dissolves at the level where entanglement defines what can and cannot coexist. The system's properties are not local possessions. They are constraints encoded in relationships. You never observe the electron alone. You observe the configuration it forms with everything it has touched. And once that reorientation settles, a sharper truth emerges. The question isn't where the electron is, but how deeply it is woven into the world around it. Approach the structure from yet another angle. Consider how quantum theory handles mutually exclusive descriptions without ever merging them into a single classical picture. The mathematical framework allows superposed states to evolve smoothly, but it never grants you a unified narrative that fits both wave-like continuity and particle-like discreteness at once. Instead, it preserves each description in a domain where the other cannot operate. You're confronting a theory that refuses to compress incompatible viewpoints into a single storyline, and that refusal is precisely what makes its predictions work. Imagine constructing a highly controlled experiment in which you gradually vary the overlap between two amplitude branches. At full overlap, interference is sharp. As the overlap shrinks, the fringes fade. Reduce it further, and the pattern becomes indistinguishable from classical noise. At no point does the system behave half wave, half particle. It adheres strictly to the logic of whichever regime the overlap permits. If you were adjusting this overlap knob, could you identify the moment the system switches conceptual frameworks, or does the transition evade every crisp definition? This reveals something deeper than a dual model. The system maintains a strict division. Coherent evolution handles possibilities, and irreversible interactions handle outcomes. Each regime follows its own laws, and trying to blend them creates contradictions that nature never produces. The unsettling part is that quantum mechanics enforces this separation flawlessly, yet your intuition insists on a continuity that has no physical counterpart. You want the electron to be something in the interval between leaving the source and hitting the screen. The theory refuses that request. Push this further. The dual structure isn't a flaw to be resolved. It's a boundary condition that limits what any description of the world can claim. You're witnessing a point where human categories fail, not where physics breaks. And once you accept that limit, a sharper realization solidifies. The mystery persists only because you keep demanding a single story where nature offers none. Begin from a viewpoint broad enough to contain every thread you've followed so far. Coherence, distinguishability, decoherence, entanglement, amplitude, evolution, measurement asymmetry. When placed side by side, these ideas seem like different mechanisms, yet they converge on one underlying structure. Quantum theory does not assign properties to isolated entities. It assigns constraints to entire configurations. The tension you've been tracking emerges not from ambiguity in the electron, but from the incompatibility between global rules and the local snapshots you try to extract. You're asking for a picture that the framework refuses to compress. Imagine suspending the entire double-slit setup inside a larger quantum device where the slits, detectors, and even parts of the screen are themselves coherent elements. In that regime, the system is no longer a particle moving through apparatus. It is a single evolving state defined across all components. Interference depends on correlations within that state, not on what any one part does. The moment any piece becomes entangled with an external environment, the structure fragments. If you were monitoring this composite object, at what point would you decide the system has stopped being one thing and become a collection of classical parts? From this expanded perspective, the familiar dual behavior becomes a boundary effect. As long as correlations remain internal and reversible, the evolution is extended, continuous, and wave-like. Once correlations leak outward, to a detector, to thermal photons, to any macroscopic register, the state's branches separate irreversibly and outcomes crystallize. No elementary object ever switches modes. What switches is the scale at which correlations can be neglected. Your classical intuition depends on that neglect, but the quantum description never abandons the full structure. This synthesis exposes a deeper coherence. All earlier puzzles stem from forcing local narratives onto global dynamics. You want the electron to bear its properties alone. The theory insists those properties arise from relationships. You want a trajectory. The theory offers coordinated amplitudes. You want certainty embedded in the object itself. The theory locates it only in the interaction you enforce. Seen this way, the long-standing tension resolves into a different kind of clarity. The behavior you observe is the visible trace of a much larger architecture you never directly perceive. Shift to the simplest possible frame. An electron travels from source to screen, and every attempt to pin down what it really does collapses into contradictions. Across all the layers you followed, coherence, entanglement, informational boundaries, environmental imprinting, one conclusion survives unbroken. No single description can capture the system from start to finish. The wave-like evolution and the particle-like detection are not competing pictures. They are complementary phases of a single process that cannot be compressed into classical terms without tearing its logic apart. Imagine a version of the experiment where you remove every detector, every environmental disturbance, every trace of distinguishing information. The electron propagates as an extended amplitude structure. Now reintroduce a single interaction that can, in principle, reveal a path. The entire behavior reorganizes instantly. One adjustment reshapes the full network of correlations. If you were standing inside that setup, you would feel the shift not as a change in the particle, but as a change in the questions the world permits you to ask. This brings the arc to its final point. The system is not both here and there in the way classical intuition demands. It occupies a structure in which here and there are not yet meaningful distinctions. Those distinctions arise only when you force the world to deliver a definite answer. The apparent duality is the residue of imposing classical categories on a framework that does not bow to them. In the end, the phenomenon does not tell you what the electron is. It tells you what your questions carve out of reality.